Swayam Prabha. Digital India. Educated India.
Morning everyone. Today we are going to finish up on our topic on this temperature measurement, which is a part of our module 10, and we are going to end up with the week number 10 during today's lecture. Now we already had 2 lectures on this particular topic where we have discussed about 3 different approaches of temperature measurement. Like if you remember, during the first lecture on this particular week, we have categorized the different methods of temperature measurement broadly into 5 categories, out of which the first 2 very common categories, like the measurement based upon the volume expansion or change in geometric dimensions, and also the change in gas or vapor pressure, were discussed in the first lecture. Like under the former category, we talked about 2 very common methods, the bimetallic straps or bimetallic strips and the liquid in glass thermometer, whereas in the second category we mostly talked about the pressure thermometer. Actually discussed about that very briefly, and in the previous lecture we discussed about the methods based upon some change in some electrical quantities. There we had 3 different kinds of methods which are extremely popular for industrial applications, like the RTD or resistance temperature detector, the thermistor, and also thermocouples. As a quick recap, in case of RTD, we generally use some kind of metals, and as the temperature changes, the resistance of the metal also changes. Now if that sensor is forms a part of some kind of bridge circuit which is initially under balance situation, then any change in the resistance will cause a deflection, and so we have to put some effort to get it back to the null situation. So we can operate the device either in deflection mode or null mode, both of them providing a way of measuring the change in the resistance and subsequently a change in the temperature. RTDs are very good devices. They are very stable in operation, has a very large temperature range, can easily go up to 800 to 1000 degrees Celsius. The other one is thermocouples, which actually operate in opposite way to resistors, or I should say RTDs. In case of RTDs, we have positive temperature coefficient of resistance, that is, with increase in temperature resistance increases, whereas in case of thermistors more commonly we have negative temperature coefficient, that is, with increase in temperature resistance decreases very sharply. The magnitude of the temperature coefficients can be 1 or 2 order higher for thermistors compared to RTDs, thereby providing excellent option for identifying even very small change in temperature. We can also have our thermistors with positive temperature coefficient. These generally are semiconductor type materials, and again provides very high sensitivity. However, the problem with thermistors generally is a much smaller temperature range. And the third one that we have discussed is thermocouple, probably the most common temperature measuring option in industries, where we make use of the Seebeck effect through a temperature through a couple of 2 dissimilar metals. One end of the couple is kept at the point where we want the temperature measurement, other end is kept at some other temperature, generally a lower temperature, and so the EMF produced by this gives a measure of the corresponding temperature. Our thermocouples are very cheap device. We can get a point measurement, which is probably not possible with any of the other methods talked about so far, and also they are generally quite rugged, can cover a very decent temperature range. However, thermocouples generally require a cold junction compensation to get a accurate reading. As we move on, today we shall be solving a few numerical problems first in relation with all those electrical components. And the first problem there, just read it out. Here you are talking about a resistance thermometer. It is to be constructed of nickel wire. Thermometer resistance at 20 degrees Celsius is 100 ohm. If the resistivity of nickel is 0.8 milliohm per meter. Please be careful about the way I have written this. Here there are two m's on either side of ohm symbol. The first one refers to milli, so that is just a prefix to ohm, whereas the second one is meter. There is a dot in between, so be careful the way we are writing this. So it is 0.1 milliohm per meter or into meter, and we have to find the required length for wire diameters of 0.4 meter, 0.4 millimeter and 2 millimeter. Then there is a second part, I shall be coming back to that shortly. So we have a resistance thermometer, basically an RTD made of nickel. So we have initial temperature, say we can write T naught to be equal to 20 degrees Celsius, and corresponding reference resistance is equal to 100 ohm, and the resistivity, which commonly is written as rho, is given as 0.8 into 10 to the power minus 3 ohm meter. Now we have to calculate the length of this resistor. Now what is the definition of resistivity? Is actually a very simple question. At least for the first part we do not have to use any concept of temperature measurement, it is just the definition of resistivity. We know that as per the definition, resistivity, or sorry, the resistance R is written as rho L by A, where L is the length of the resistor and A is the cross section area, or if we make use of the diameter, then it is rho L divided by pi by 4 d square, that is 4 rho L by pi d square, or if we take length out, so we have pi r d square by 4 rho. So it is a very straightforward situation. At least for the base case, we can maybe writing R naught for this, for the initial situation. So R naught is given as 100 ohm, resistivity is given as 0.8 to 10 to the minus 3 ohm meter, and there are two different values of diameter given. So if you put D equal to 0.4 millimeter, that is 4 into 10 to the power minus 4 meter, then you can do the calculation. For the first case, you are going to get L equal to 0.0157 meter, whereas if we are putting D equal to 2 millimeter, that is 2 into 10 to the power minus 3 meter, then we are going to have L equal to 0.39 meter. So you can see that with change in the value of this diameter, how drastically the corresponding length required that changes. And generally we always want the size of the sensor to be very small, so that we can get quite local measurement, and also the bulk of the device is much smaller. So it is essential that we use wires of very small diameter. Like in the first case, where the diameter is just 0.4 millimeter, only a 15 mm length is sufficient, whereas in the second case we need a much larger length, about 39 centimeter, which is significantly larger compared to the first case. However, the diameter is increased only 5 times. So now go to the second part of the problem. It is said that if the resistance varies linearly with a sensitivity of 0.2 ohm per degree Celsius, what would be the resistance at 100 degree Celsius? So here we can make use of the simple relation for RTD. It is said that the resistance varies linearly with a sensitivity of this much. So the change in resistance with temperature follows a linear relation, which we can represent something like, say, RT is equal to R naught into 1 plus alpha into T minus T naught, where T naught is the reference temperature. Now in this case R naught is given as 100 ohm, and alpha, which is the sensitivity, that is given as 0.2 ohm per degree Celsius. So actually I have written it wrong, the relation, because sensitivity is given in terms of ohm per degree Celsius. In that case, this one should be written as RT is equal to R naught plus alpha into T minus T naught, where T naught refers to the reference temperature, R naught is the corresponding reference resistance. Actually we have used capital T to represent the temperature. Truly speaking, we should have written small t, because generally the symbol capital T we reserve for temperature values in Kelvin, that is absolute temperature, but here we are talking about temperature in Celsius. So, rest is quite simple. We can easily choose T naught to be equal to 20 degrees Celsius and corresponding R naught to be 100 ohm. So, if you put the values, then we are talking about a resistance of 100 ohm plus sensitivity of 0.2 into, we want to calculate corresponding to 100 degrees Celsius minus T naught is 20 degrees Celsius. So, if you put the numbers, then you are getting 100 plus 0.2 into 80, that is 116 ohm. So, with change in temperature from 20 degrees Celsius to 100 degrees Celsius, for this particular RTD, the resistance is changing by 16 ohm, which is quite significant. That is a very simple situation in RTD. Let us deal with another one. Here our problem is slightly different. Here we are talking about a pulse excited resonance thermometer. It is subjected to a rectangular pulse of 100 volt height and 0.1 second duration. The pulse is on for 0.1 second and off for 0.9 second in a repetitive cycle. Now, that is quite interesting. Here we are saying that the RTD is exposed to some time varying voltage signal, and the time varying signal is of the shape of a rectangular pulse. That means the excitation voltage, if we plot with respect to time, say time on this axis and excitation voltage on this axis, then this excitation voltage will be of a shape like this. For a 0.1 second duration, it is a constant value of 100 volt, then for remaining 0.9 second there is nothing, and so this duration is 0.1 second. Then if we say up to this is 0.9, nothing during this period, then again another rectangular pulse appears, and which is again of the same duration, that is 0.1 second, and this particular height of each of these pulses is equal to 100 volt. So, we are talking about a periodic signal having a time period capital T of 0.1 plus 0.9, that is 1 second. Out of this, for 0.1 second we have a constant voltage signal of 100 volt and nothing for the remaining 0.9 second. So, we have to calculate the average power this voltage pulse would produce in a 500 ohm resistor. So, the resistance is 500 ohm and we have to calculate the average power corresponding to this signal. Again, it is not strictly a question related to RTD, but this is more related to application of any resistance based devices. Whenever you are talking about a periodic signal, then instead of working with any values, we have to calculate the corresponding RMS voltage. Now, what can be the your RMS value in this case? So, E RMS can be equal to 1 upon time period into root over of integral 0 to t your E dt, or I should say E square dt, because we are taking RMS. Now, this integration can be divided into two parts, that is 0 to 0.1 E square dt plus 0.1 to 1 E square dt whole to the power half. Now, for 0.1 to 1 the signal is off. So, this part cancels out, and during the first part 0 to 0.1 the signal is on, having a constant value of 100 volt. So, E square is a constant during that part. So, it becomes a very simple situation, 1 by t into 100 square into 0.1 and t is equal to 100, of course whole to the power half. So, if we calculate the value, your RMS voltage is going to be coming as 31.62 volt. Quite often, may not be in this problem, but we may be generally is interested in knowing this ratio of E RMS to E peak of the periodic signal. Here RMS value is 31.62 volt and your peak voltage is 100 volt. So, you can get the corresponding ratio. But our objective is not to get this ratio, rather we want to calculate the average power. Once you know the RMS voltage, the average power calculation is very easy, because your corresponding average power will be just E RMS square divided by resistance. So, 31.62 square divided by, we are having a 500 ohm resistor, and corresponding value will roughly be equal to 2 watt, which is going to be your solution. So, these are simple situations with RTDs. Let us now move to a problem involving thermistors. Here our question is, just carefully read it out. We are talking about a thermistor having a beta equal to 3450 Kelvin and resistance at 20 degrees Celsius is known to be 1 kilo ohm plus minus 2 ohm. So, there is an uncertainty involved. At the reference temperature of 20 degrees Celsius, the corresponding reference resistance value is 1 kilo ohm with an uncertainty of 2 ohm. So, now for an RTD, what is the relation with temperature? We know that for RTD the temperature relation is given as RT equal to R naught into exponential beta into 1 by T minus 1 by T naught or log of RT by R naught is equal to beta into 1 upon T minus 1 upon T naught. So, if we want to express this one in terms of temperature, then we are going to get 1 upon T minus 1 upon T naught is equal to 1 by beta into ln RT upon R naught, that is 1 upon T is equal to, I guess we derived this thing in the last class, but I do not have it with me. So, I am just getting a direct relation in terms of temperature, or T is equal to 1 upon T naught plus 1 upon beta into ln RT upon R naught whole to the power minus 1. We could have represented in any other ways also, but now look at the problem. Here it is given that your reference temperature T naught is 20 degrees Celsius, or in this problem it is better to convert this to SI units. So, it is 293.15 Kelvin. Corresponding reference resistance value is 1 kilo ohm plus minus 2 ohm or 1000 ohm plus minus 2 ohm. It is and the beta value is given as 3450 Kelvin. It is in contact with a specific surface, its resistance is measured to be 2.5 kilo ohm with an uncertainty of plus minus 5 ohm. So, this plus minus 5 ohm is coming as the uncertainty during the modified resistance measurement, and we have to calculate the constant temperature and the maximum error, that is the uncertainty in this temperature measurement. So, here we are talking about an RT value of 2.5 kilo ohm plus minus 5 ohm or 2500 ohm plus minus 5 ohm. So, to find the value of the temperature, the nominal value, we have to put the nominal values here, that is we have to put R naught equal to 1000 ohm and RT equal to 2.5 kilo ohm or 2500 ohm in this particular relation, and if we put that, the value of the temperature is going to come as 271.845 Kelvin. Remember here T naught and is used in Kelvin, beta is given, and RT and R naught we have used their nominal values 1000 and 2500 respectively, or I should say RT 2500 and R naught is 1000 ohm, because we have to calculate the nominal value of the temperature. Now, you have to calculate the uncertainty. Just think about in the very first week how we have learned of calculating the uncertainty, the same principle we have to make use of here. We have uncertainty involved in the measurement of beta, no, not in the measurement of beta, but we have uncertainty involved in the value of RT and R naught, not in the value of beta and T naught. So, we have to calculate then the corresponding sensitivities, that is dou T dou RT. How much will be that if you calculate this? So, it is going to be minus 1 into this whole thing 1 by T naught plus 1 upon beta ln RT by R naught whole to the power minus 2 into, if we go inside this now, into 1 upon beta into R naught by RT, or we can probably write this one as minus R naught by beta T square RT. So, corresponding value you can calculate. Similarly, dou T dou R naught you can differentiate with respect to R naught and get the corresponding calculation for this. So, once you get both the calculations done, then the total uncertainty involved will be equal to the root of dou T dou RT into the uncertainty involved in RT measurement whole square plus dou T dou R naught into uncertainty involved in R naught measurement whole square. In this particular problem, I just have the final value which is 0606 Kelvin. So, the final temperature that we are going to get, that is actually going to come as 271.845 plus minus 0.061 Kelvin. This is nominal value and this is the uncertainty involved in this for the given thermistor. Again, we are just using this particular concept of thermistor, rest of the problem you already know from your earlier discussions. And finally, we shall be rounding off with a small problem on the use of thermocouples. During the calibration of a new thermocouple, 5 millivolt and 25 millivolt of EMF were obtained at boiling point of water and boiling point of sulfur with a cold junction at 0 degree Celsius. So, we are talking about the calibration of a thermocouple. And during the calibration process, the cold junction is maintained at this particular temperature and the hot junction is taken in contact with two standard temperatures. One is the boiling point of water which is 100 degree Celsius, and other is the boiling point of sulfur which is 445 degree Celsius, and corresponding EMFs have been measured. So, assuming this following relation, we have to determine the hot junction temperature for an EMF output of 2 millivolt with the cold junction at 40 degree Celsius. So, before proceeding, let us try to make use of the given relation and identify the corresponding value of these constants or coefficients A and B. So, in the first case, your T1, the cold junction temperature is 0 degree Celsius. Here it is also given these temperatures are in Celsius. All these T1 and T2 are in Celsius, otherwise you should have converted in Kelvin, but for the given relation it is specifically mentioned that the values of T1 and T2 are in Celsius. So, for the first problem T1 or for the first calibration point, T1 is equal to 0 degree Celsius, T2 equal to 100 degree Celsius, and corresponding EMF is equal to 5 into 10 to the power minus 3 volt. During the second calibration, our T1 is equal to 0 degree Celsius, T2 equal to the boiling point of sulfur which is 445 degree Celsius, and EMF is equal to 25 millivolt, that is 25 into 10 to the power minus 3 volt. So, we can combine this to get the values of A and B. We can get some numbers corresponding to A and B. I do not have the values, so I am not writing it here. You can easily solve it by putting the values of T1 and T2 and get the corresponding two equations. Now, using this relation, we have to calculate the hot junction temperature for an EMF output of 2 millivolt with a cold junction at 40 degree Celsius. Means the second situation we have, or third situation I should say, T1 is given as 40 degree Celsius, T2 is unknown, the one that we have to find, and the EMF is mentioned to be 2 into 10 to the power minus 3 volt. Now, the question is the calibrations that were done corresponding to the value of 0 degree Celsius. Then how can we make use of this? We could have directly obtained the value, but there is a better way of doing this, that is, I hope you remember the laws of thermocouple that we have discussed in the previous lecture. Here we shall be using the laws of the intermediate temperature. See, the EMF corresponding to 0 to 40 we can easily calculate by putting the values of E into 40 minus 0 plus B into 40 square minus 0 square is equal to something you will be getting based upon the values of A and B. And in the second case, EMF corresponding to 0 to some unknown temperature T, that will be A into T minus 0 plus B into T square minus 0 square, again something you are going to get. Now, what we know from our previous discussion about the laws of thermocouples, then EMF corresponding to 0 to 40 plus EMF is corresponding to 40 to some t should be equal to EMF corresponding to 0 to t. Here EMF corresponding to 0 to 40 to t is given. So, if we put those values, EMF 0 to 40, for our notation it is 40A plus 1600B plus EMF corresponding to 40 to t, that is given as 2 into 10 to the power minus 3, that will be equal to AT plus BT square. As A and B values already you have calculated here. So, putting this, you are going to get the value of T, and in this case T is going to be coming as 79.8 degrees Celsius. Remember, here we are using T as Celsius only, because the relation, the given relation specifically states that the T is in Celsius. So, this is the hot junction temperature. For the second case, it is mentioned that we have to find the EMF for a temperature pair of 540 degrees Celsius. Again, we can follow the same procedure. For EMF corresponding to 0 to 40 can be calculated, EMF corresponding to 0 to 500 can be calculated, then EMF corresponding to 40 to 500 will be equal to EMF corresponding to 0 to 500 minus EMF corresponding to 0 to 40, and that is going to give you the result. The answer that you are going to get in this problem is 26.6 millivolt. So, you can do the calculation, get the values of A and B, and putting them you can try to find these two values. So, these are certain example problems related to the electrical thermometers, which are very common in applications, and I am sure you will be using this not only in your laboratories, but later on also when you join the industries. Let us quickly discuss about a few more temperature measuring options before I close on this particular topic. And among electrical properties or changes in electrical property based measuring devices, we have discussed about three, the RTDs and thermistors, which uses the principle of resistance change with temperature, whereas we have also discussed about thermocouple, which makes use of the Seebeck effect. However, there is a fourth option also. Thermistor commonly is called bulk semiconductor sensors, where there is something known as the junction semiconductor sensor or semiconductor junction sensors. These are nothing but diodes. As we know from your knowledge about physics, that as the temperature changes, the performance of diode also changes, both during the forward bias and reverse bias, and the voltage output from a diode keeps on changing. Just the same principle is used. So, we can make use of a very simple diode, take it in contact with the surface where you want the temperature measurement, and by noting the corresponding change in temperature, which is generally very linear, you can easily get the change in voltage, I should say, we can easily get a measurement of the corresponding temperature of the surface. It has several advantages, like it is very small in size. You know how small a diode can be. So, these are small devices, they are extremely sensitive to small change in temperatures, and they provide very linear output, something like this. During forward bias, like shown here, as the temperature is dropping, the corresponding voltage also keeps on increasing. High accuracy we can get from them, almost comparable to the thermocouples or even better than thermocouples sometimes. Low power consumption, particularly if you compare this one to RTDs and thermistors, the power consumption is quite low. No signal conditioning required like in case of thermocouples. We can use this one in analog circuits to get analog output, also we can use them to produce digital outputs, or even sometimes logic outputs, like something just like yes and no kind of outputs also can be produced from them. They are often combined in a chip or IC to get multiple operations done parallelly using the same circuitry, and we can have a wide range of secondary application of such kind of devices. Several control applications, switching kind of applications, sensing some surrounding temperature, warning systems, all of them can have this kind of junction semiconductor based sensors. But there is one big disadvantage, that is its temperature range is very small, only about -50 to 150 degrees Celsius, and they are generally costlier than the thermocouples. Despite having low power consumption, they can be much more costlier compared to thermocouples and thermistors both. So, these are electrical property based devices. This is a summary of the 4 that we have talked about. Just their advantages and disadvantages are listed here, and also the voltage versus temperature plots are shown. As you can see that the integrated circuits based sensors, or the one I just talked about, the junction semiconductor sensors, are giving very linear output. That is why they are the most linear kind of device. However, the most stable output and most accurate operation we can generally get from the RTDs. But the output from RTDs are generally quite small in magnitude. We often have to go for some kind of amplification, whereas in case of thermistor we get the high output. Probably for a given change in temperature, thermistor gives the highest output mostly. Also, thermistors are generally much faster compared to the other one. Actually, it is mentioned that IC based devices also give the highest output, but thermistors also are comparable with them. Definitely they are much greater in magnitude compared to the thermocouples and RTDs. Thermocouples have several disadvantages, like non-linearity is one disadvantage, voltage output is quite low, they are much less stable and less sensitive compared to RTDs. We need a reference temperature. However, their biggest advantage is their simplicity, inexpensiveness and ruggedness, and also they can give very high temperature range, particularly if you compare with thermistors or IC based sensors. That is, if we compare them with semiconductor based devices, they give a very wide range. RTDs also can give a very wide range of help in wide range of operation, particularly considering that their operation or output is very more linear compared to thermocouples and also compared to thermistors, but their problem is they are expensive. We need a current source and self-heating problem, the I square R loss that can be significant, particularly the lead wires loss also can be quite significant with RTDs. Thermistors, the problem is the non-linearity in the output and the limited temperature range, and also their fragile nature and self-heating related issue quite similar to RTDs, but their advantages are this high output and extremely fast response, particularly if you want to use in some kind of feedback circuits or some kind of temperature control application. Thermistors can be very good option. And IC based sensors, their advantage are their very linear output and highest linear output and also highest output, and very inexpensive comparably with thermocouples, sometimes even cheaper than thermocouples. Their problem is this particular temperature range and the requirement of power supply, and they are quite slow, probably the slowest among all 4. So, each of them has their own area of application. Like if we are looking for an option for long term operation, very stable output and very accurate output, we should go for RTDs. Whereas if we are looking for some kind of control application, fast output, probably thermistors are better option, at least as long as you are at the low temperature zone. Thermocouples can cover a very high operating temperature zone. So, if you are looking for applications which are quite rough and you have a large temperature span and you want to measure temperature at several points, thermocouples are ideal compared to RTDs. And if we specifically need a very linear output at low cost, then IC based sensor or bulk junction semiconductor sensors probably are the better option. So, with this we move on to the next category, where we shall be talking about the use of emitted radiation from bodies for temperature measurement. Now, we know that when we want to measure the temperature of a surface using say an expansion based device like a liquid in glass thermometer, we have to take the thermometer in contact with that surface, at least the bulb of the thermometer, also preferably a significant portion of the stem of the thermometer should be in contact with the surface where you want the temperature measurement. And then the thermometer itself will take some time to respond, slowly acquiring heat from the corresponding surface or losing heat to the surface if it is at a lower temperature, and then the liquid column will keep on moving within the capillary tube, settling down after a certain period of time. So, we have to bring the thermocouple. The important part is we have to bring the thermometer in contact with the surface, and also we have to wait for some time. What about the electrical based sensors? The same issue still persists. For electrical based sensors or for pressure thermometer, we have to bring the sensor part in contact with the surface, The rest of the components can be a distance apart, particularly if we are using a significantly long lead wire in case of RTDs or thermocouples, or if we are using a long capillary tube in case of pressure thermometers. You can go for some sort of distant measurement or remote measurement, but still some part needs to be in contact with the surface. But now if that is not possible, then what will happen? Like, think about if we want to measure the temperature of the stars, the temperature of the sun, which is the closest star or the star closest to our planet at least, then how can you measure the temperature of that? Or maybe something which is within your grasp, but still you may not have an option of measuring that temperature. Like, say, how can measure the temperature of the fire inside, say, a combustion chamber or a furnace? Quite often the combustion chambers can have temperature of 2000 Kelvin or higher than that, and none of the known materials can sustain that level of temperature for a prolonged duration of time, and that is why we can't use any of the discussed methods for such level of temperature measurement. We have to necessitate an option for remote temperature measurement, truly remote temperature measurement, where every part of the device will be away from the measuring zone or the measurement zone, and that is why where the radiation based devices, which are commonly called pyrometer, they comes into picture. We know that any body at a temperature higher than absolute 0 emits some radiation depending upon its own temperature level. The temperature level of emission depends upon the, or I should say the level of emission, the wavelength of emission depends upon the temperature of the source. The radiation waves can be classified into several categories depending on the magnitude of wavelength. Like, for extremely small wavelength we can have ultraviolets, whereas if we move to longer wavelengths or shorter frequencies, then we shall be having X-rays, then UV rays, then we have a very small visible spectrum band, and then comes infrareds, which are much longer wavelengths and lower frequency signals compared to the ultraviolets ones or X-rays. Now, exactly which kind of radiation a body is going to emit, that depends on the temperature of the body. Like, the most ideal one that we can have is a black body which emits radiation independent of the wavelength of the corresponding radiation. Rather, whatever emission that comes out of a black body is a sole function of the corresponding temperature only. Similarly, any radiation falling on a black surface, that gets totally absorbed. Now, whenever you are talking about radiation, generally two terms comes into picture. Radiation is dependent on temperature, radiation emitting from a surface is dependent on the direction, and also it depends on the wavelength. So, accordingly we use the term spectral and directional. Spectral refers to the dependence on wavelength, whereas directional dependence indicates the dependence on the direction. If we are working in a spherical coordinate system, then it depends on the value of theta, the zenith angle, and the phi, the azimuthal angle. In corresponding to spectral, we have another term which is called total. Total refers to integrated over all possible wavelengths from 0 to infinity, as waves or electromagnetic waves can have wavelengths ranging from 0 to infinity, and so once we integrate a corresponding spectral quantity over the entire spectrum, what we get, that is called the total. Similarly, if we integrate over all possible directions, then what we get, that is called hemispherical, because then we are talking about integration over along all possible rays of a hemisphere, where our integration will be phi equal to 0 to 2 pi, zenith angle theta equal to 0 to pi by 2, and then corresponding quantity sin theta cos theta d theta d phi. These are very standard proofs. You can refer to any standard heat transfer book to get the origin of this particular relation. But hemispherical refers to emissions going in all possible directions over an hemisphere. Now, if I lambda E refers to the intensity of emission coming out of a surface with an wavelength of lambda, then this is generally a spectral directional variation because it depends on lambda, theta and phi, or to be more specific, it also depends on the temperature of the surface. So, this is a spectral and directional quantity which we have the dependence on the wavelength and also dependence on the all possible directions. Now, if we integrate this over all possible directions, that is phi equal to 0 to 2 pi, theta equal to 0 to pi by 2, sin theta cos theta, d theta d phi, then what we get, that we generally indicate as E lambda, function of lambda, which is we call the spectral emissive power, or I should say the spectral hemispherical emissive power, because here we are talking about emissions of one particular wavelength, but going into all possible directions over a hemisphere. And now once we integrate this one over all possible wavelengths, then what we get is the total emissive power. Actually it should be a function of temperature, and this is also a function of temperature, because theta phi dependence goes off once we do the integration and lambda dependence goes on once we do this second integration. So, this is spectral emissive power or spectral hemispherical emissive power. This is total hemispherical emissive power, that is the total amount of radiation that can be emitted from the surface of a body maintained at a temperature T. When you are talking about a black body, that is for a given temperature, that is the maximum emission that we can get from this particular surface, but the emissive power that keeps on varying with the temperature of the surface. If we plot that, then we are going to get a curve like this, where we have the wavelength lambda on one side and spectral emissive power or E lambda b, that is why I just talked about, that is on the other side. Now, depending on the temperature of the source, you can see that each of them is taking some parabolic kind of shape. For lower temperature, the wavelength is also quite low, but as the temperature keeps on increasing, corresponding wavelength increases, and beyond 1000 Kelvin the change is also quite significant, but for lower temperatures probably the change is much more dominant. And this particular relation is given by this, where on the left hand side we have the spectral hemispherical emissive power, which is given by a relation like this. Here C1 and C2 are constants. C1 is equal to 2hc square and the value is generally 374.18 megawatt micrometer to the power 4 by meter square, where h is the Planck's constant. I hope you can remember that the Planck constant general is presently sets the new standard for measurement of mass. Small c refers to the velocity of light in vacuum, and C2 is hc by kb, where again h and c are respectively Planck constant and the velocity of light in vacuum, and kb is the Boltzmann constant, and the value of C2 is 14388 micrometer Kelvin. Be careful, here we are writing this unit micrometer instead of writing meters, because wavelengths are always very small, often in the range of micrometers. So, C1 and C2 are given, and now if we want to know the value of total emissive power from this surface, then it will be equal to integrated over 0 to infinity, and this total hemispherical emissive power is a function of temperature. Now, for a given temperature of the surface, if we our interest is to calculate where we get the maximum value of this emissive power, or corresponding to which wavelength at least, then we have to differentiate this expression with respect to lambda with t remaining constant and equate that to 0. If we equate that, then we get the very well celebrated relation known as the Maxwell's displacement law, or it is called the Wien's displacement law, where the first one is this particular one is the Planck's relation, whereas what we are writing here is called the Wien's displacement law, where for a given temperature, the product of the temperature and corresponding maximum corresponding wavelength at which we get the maximum spectral emissive power, that is a constant, and the value of the C3 is 2898 micrometer Kelvin. So, this sets up the basis for the temperature measurement using the radiation based devices. We know that as the temperature of the surface keeps on changing, corresponding emissive power will also keep on changing, and for it will of course depends on the wavelength. So, if we can analyze the wavelength for a surface, then we can also, or I should say analyze the wavelength corresponding to the emission coming from a surface, we can also calculate the corresponding temperature of the surface. But the relations that I have written here, these relations are available, or these relations are valid for black bodies, but in practical case when you are talking about real surface, then you have to define something known as the emissivity. Emissivity is given as the spectral emissive power for a real surface divided by the spectral emissive power of a black body, or I should say the spectral hemispherical emissivity is defined as spectral hemispherical emissive power for a real surface divided by the spectral hemispherical emissive power of a black body. Estimation of this epsilon is very important for any real radiation based measurement. Now, the principle is that whenever a surface is emitting certain radiation, then we shall be using some kind of detector which is going to sense that radiation. Now, energy is coming to this particular sensor in the form of radiation, accordingly its temperature increases, but it will also lose energy to the surrounding in the form of its own emission, and there may be convection from the surrounding air if there is anything at all. If there is no convection or conduction heat losses, then it will also keep on emitting depending on its own temperature. Accordingly, there will be change in the temperature of the sensor, and after some time it will reach certain equilibrium position or equilibrium temperature, and under which condition the emission coming from the source and the emission going out of this particular body should be equal to each other, so that the temperature is maintained constant. So, then applying an energy balance, we can easily sense the temperature of this temperature of this particular source, as we are continuously measuring the temperature of this particular body using any of the method that we talked about till now, like thermistors. For this purpose, we generally, depending on which wavelength we are interested in, we can use different kinds of filters, like shown here. If our interest is low frequencies, then we use low pass filter, where the wavelengths corresponding to low or corresponding to low wavelength, they are allowed to pass, but those having higher wavelength, they are not allowed to pass. Similarly, for high pass filter, those are having higher wavelengths are allowed to pass, but low wavelengths are not allowed to pass. We can also have a band pass thing, where only within a range of wavelengths the waves are allowed to pass, or the opposite of this in the form of this band stop, and several combination of this. There are different materials which represents varying levels of absorptivity depending on their configuration. We know that whenever emission falls on a surface, or I should say irradiation falls on a surface, the irradiated energy can have three different fates. It can get absorbed in the surface, it can get reflected from the surface, or it can just get transmitted through the surface. Accordingly, we can write alpha plus rho plus tau is equal to 1, where alpha refers to the absorptivity, that is the fraction of the irradiated energy which gets absorbed by the surface. Rho is reflectivity, it represents the fraction of energy which gets reflected, and tau is the transmittivity, which represents the fraction corresponding to transmission. For a perfectly black surface, we generally have alpha equal to epsilon, which is called the Kirchhoff's law, that is emissivity and absorptivity are equal. For practical surfaces, like if you are talking about an opaque surface, in that case tau is equal to 0, so that alpha plus rho is equal to 1, and accordingly which wavelengths it is going to, but the values of both this alpha and rho that varies with the wavelength. So, depending on which wavelengths we are going to talk about, accordingly we can select different kinds of filters. Like Pyrex glass generally allow radiations of within the wavelength of 0.3 to something like 2.7 micron to pass through and blocks everything else. So, if our interest is low frequency or sorry low smaller wavelengths, then this one can be a good filter option. Whereas, calcium fluoride generally allows wavelength in the range of 0.3 to 10 micron to pass through. So, it can be a high pass kind of filter, it can act as a high pass filter. Now, the selection of the pyrometer from, or I should say the selection of distance of pyrometer from the object needs to be considered if you needs to consider a few practical limitations. We know that pyrometers can give you remote temperature sensing, because as we are sensing radiation. So, theoretically speaking, the radiation that is coming from the source and falling on your sensor, that is independent or not changed by the medium which is in between. However, there can be several other factors which can decide this distance, like the greater the distance, more degree of averaging we have to go for, because the emission coming from the source gets scattered in all possible directions, thereby only a small fraction may reach your sensor. So, you have to go for some kind of averaging. The nature of intervening atmosphere, while we generally consider the atmosphere to be non-participating, but presence of certain gases like carbon dioxide or water vapor, that they can absorb significant amount of radiation. Also, the presence of dust or moisture particles can lead to reflection from the medium itself. So, if such kind of participating media is present, then a significant portion of the radiated or the initial irradiation coming from the source may get lost. The heat radiated from the surrounding bodies also can affect your reading, because your sensor often is not able to recognize the difference between the emission coming from the actual source and the emission coming from some unwanted surrounding object. Uncertainty involved in the source emissivity is a big factor, as I have just mentioned. So, that we need to have a proper idea always. These are just some kind of common radiation measuring instruments. The first one is the total radiation pyrometer, which is something like a total measure over all wavelengths, that is no filter used, emissions of all wavelengths are allowed to come. So, as the radiation enters from this side, it generally gets reflected by a mirror. The mirror is adjusted such that it all the emissions are allowed to meet in a particular focus, and we keep some thermocouple or some other kind of temperature measuring device there to measure the temperature of temperature at this point, and then using the energy balance we can easily get the temperature at this particular location. Total radiation pyrometer or any such kind of radiation pyrometer has a host of advantages, like can be used for very high temperature. We can easily go for 2000 or 3000 degrees Celsius or even beyond that, because we are talking about a temperature balance. So, never assume that the temperature of this thermocouple is going to be equal to the temperature of the source. It will be much lower than this, because it is receiving only a small portion of energy, but as you are using the energy balance, so accordingly its temperature will be an indicator of the source temperature. Substantially high output signal we can get here, which was a problem in case of thermocouples, etc. Non-contact type operation, which is the biggest advantage for any kind of pyrometers. Moderate cost, reasonably accurate these are, and quite fast response, at least faster compared to the liquid in glass kind of thermometers or sometimes the RTDs even. But the problem is nonlinear response, because the total emissive energy or emissive power that is coming out of a surface is not linearly dependent on its temperature. Like in the previous slide, I have written the relation for E lambda B using the Planck's relation. Now, if our interest is to know the total emissive power, we know that this one is a function of temperature and the wavelength. Now, if we integrate this one over 0 to infinity, that is all possible wavelengths, then the result that you are going to get, that generally is some constant into t to the power 4. What is this relation known as? This is the well celebrated Stefan-Boltzmann relation, and the sigma is Stefan-Boltzmann constant, whose value is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So, the emissive power coming from a body is actually proportional to the fourth power of temperature. Therefore, as the temperature changes, emissive power can change significantly and thereby providing highly nonlinear response. There are several factors involved, as we have mentioned. Surrounding radiation from the surrounding sources can also affect the performance. Uncertainty in emissivity is a problem in any kind of pyrometers, and presence of participating media. Again, all these actually are problem for any kind of radiation based pyrometers. Next one is an optical pyrometer, which is also commonly known as a disappearing filament pyrometer. It is a very interesting situation. Here we have one bulb filament. From the temperature source, whatever emission is coming using some kind of lens, that is allowed to focus at the filament, specifically at the filament, and then using this eyepiece, observer keeps a focus on the filament. The eyepiece generally is adjusted so that the filament and the temperature source, they are seen on the same line. Now, the temperature of the filament can be changed by changing the setting of this rheostat. So, accordingly the emission from this filament can also be modified. We can easily increase this one or decrease this one. Our idea of the observation here, it is a purely observation based device. So, our idea is something like this. When the filament is visible in dark compared to the main source, then the filament temperature must be lower than the temperature of the source. When the filament is appearing lighter compared to the source, then it must be at a higher temperature, because it is emitting more white light or emitting more from the whiter section of the visible spectrum. So, it must be at a temperature higher than the source, and if both temperatures are exactly equal, then as you can see, where is the filament? Where is the filament here? The filament has vanished or disappeared. So, the temperature at which this particular observation is done, that temperature should be equal to the temperature of the source. So, this is called a disappearing filament pyrometer or vanishing filament pyrometer. It offers advantages of the simple assembly and very easy use, can go for very high accuracy within plus minus 5 degrees Celsius it can predict, which is actually quite creditable, because we are measuring something in the range of 1000 or 2000 degrees Celsius or even higher. Non-contact type measurement, distance is not an issue for this, and this is perfect for remote sensing like most of the other pyrometers. And we can also use this one to measure the heat flux, again by applying an energy balance. But problem is that as we are looking for some kind of visible emission from the filament itself, so we need to go for very high temperatures. Filament can emit some light only when the temperature of the filament goes above 700 degrees Celsius. So, we have to breach this particular temperature range to make use of this disappearing filament pyrometer, and it is not suitable for continuous measurement. But this is a kind of optical pyrometer, and it has particularly when we go beyond this particular temperature range, it is a very useful one from measurement point of view. And finally, before I go to the next device, exactly how we calculate for this optical pyrometer, we know that the emission coming from the source can be given as epsilon lambda by C1 into lambda to the power 5 into exponential of C2 by lambda into temperature of the source, that is the target temperature minus 1, will be equal to, for the filament can be assumed to be a black body, because the way it behaves. So, emissivity is equal to 1 by lambda to the power 5 into exponential C2 divided by lambda into T for the lamp or filament is 1. Now, when the temperature is lower means as long as the temperature is lower than 4000 degrees Celsius, this exponent is too large compared to 1, so that the 1 can be ignored. So, we have epsilon lambda divided by exponential of C2 by lambda into the target temperature is equal to 1 divided by exponential of C2 divided by lambda TL. So, if we combine this, so we have exponential of C2 by lambda T target temperature minus C2 by lambda T lamp is equal to epsilon lambda, which is 1 upon target temperature minus 1 upon lamp temperature, is equal to lambda upon C2 ln epsilon lambda. Here we need to have a proper estimate of this epsilon lambda. Lambda is the wavelength corresponding to which we are doing this experiment. C2, know the value of C2 as I have given earlier. So, lamp temperature is the one that we are measuring. When we are dealing with a black surface, epsilon lambda is 0, giving Tt is equal to TL. When epsilon lambda epsilon lambda is 1 for a black surface. When epsilon lambda is less than 1, that is we are dealing with a real surface, then Tt and TL they are not equal, then this particular relation provides a way of correcting the value of target temperature. So, this is an example of how we do the calculation in case of any pyrometers. And finally, I am going to finish with the infrared pyrometer. Infrared pyrometry is an option which provides us to measure quite lower temperature. Actually, when the term pyrometer we used to go for very high temperatures, well in the range of 500, 600 degrees Celsius or even higher, a few thousand degrees Celsius. But this infrared pyrometry is the one that allowed us to come to much lower temperature level, because in case of infrared we are talking about this particular wavelength range 0.7 micron to 1 millimeter, and this corresponds to a source temperature of only about 200 to 1400 Kelvin. So, we are talking about a temperature range of 200 to 1400 Kelvin. So, using this infrared temperature you can easily make use of you can easily get temperature values quite close to the normal ambient temperatures or something below that 700 degrees Celsius limit that we have seen in case of optical pyrometers. The working principle remains the same, only difference is that here we are using the infrared spectrum of light. Infrared cameras or infrared image guns are quite popular, very easily available in market, and they have you must have seen several applications of this. This is just a standard picture, but applications, have you seen this picture? Those who are interested in cricket definitely have seen this, where they call it hotspot or something, where as the ball strikes the bat or any other part of the batsman, they generally detect that by this white mark. This basically when the ball strikes a particular portion, there is a, because of the momentum transfer, there is a small change in temperature, its temperature increases by a few degrees, and the infrared camera is able to detect that particular one. It is an application. This another application, the night vision cameras, which is very common in case of animal safari or several other applications in army applications. These are or those funky shows that comes on television for ghost hunting, or they all make use of the night vision cameras, which are basically nothing but the infrared cameras. And infrared camera, though we use the term camera, but actually that is a pyrometer, because the objective is to get the temperature values over a particular spectrum. So, that takes us to the end of this particular module, where we have talked about the measurement of temperature following different principles. We started with the laws of thermodynamics, particularly the 0th and 2nd law of thermodynamics, to define the scale of the thermodynamic temperature scale. Then we categorize the temperature measuring options into 5 different categories, out of which we have discussed about the expansion based devices in the form of liquid in glass thermometer and bimetallic strips. Then we talked about the gas vapor pressure based devices in the form of pressure thermometer. Then we discussed 4 different types of electrical devices, which all are very common, like the RTDs, thermocouples, thermistors, and diode based sensors or IC based sensors. And then we talked about the pyrometers. There can be a wide range of pyrometers like optical pyrometers, total radiation pyrometer, or infrared pyrometer, depending on the range of wavelength that you are dealing with. So, that is the end of this 10th module. I hope you have got some idea about the most popular methods of measuring the temperature. Please try to solve the assignments, because I have already solved quite a few example problems in this during the course of today's lecture and also the previous lecture, and I am sure you will be able to solve the example problems or assignment problems. So, if you have any query, please keep on posting in the forum. Thank you very much.